let me begin with a word of prayer. So, Dear Father, we thank you for this day again. I thank you for this class and these students. Just ask you to guide our steps today, Lord, and just help we just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I need to talk about linear independence and the theory. So let's see, theory of differential equations. Nth order linear differential equations. I tried. Anyway, so here's the definition. If functions y1, y2, yn with domain I, some subset of the reals, all right, have c1y1 plus c2y2 plus plus cnyn equals to 0 implies on I, all right, implies that c1 is equal to 0, c2 is equal to 0, and so forth all on the way out. All right, then y1 through yn are linearly independent. And since it doesn't give us joy to write out linear independent like that, we will abbreviate this by Li. All right. So, basically what this means is if it's impossible to do this, then you've got genuinely different functions. So here's an example where it fails. If I had y1 is like, sine t plus cos t, and I had y2 was, say, sine t minus cos t, and I said y3 was, 2 sine t, well, that would be a problem, see, because y1 plus y2 is equal to y3, right? Which would give you this, y1 plus y2 minus y3 is equal to 0. So like if you look at that, what we got here is c1, oh man. Thank you. No risk, no reward. Let's see here. C1 equal to 1, C1, C2 equal to 1, C3 equals to minus 1. Right? So there you go. We have a linear combination of the functions set equal to 0, and yet the coefficients are not all 0, right? That is evidence, if you will, that these functions are dependent on one another. So they're not genuinely independent. And as we're formulating the solution set to equations in here, we must avoid this kind of dependence, all right, in order to give a proper account of our success in solving things, basically. All right, so, but there's something perverse about this example. Let me give you the perverse example while I'm at it. We could have y1 equals to t and y2 equals to the absolute value of t, right? So you notice that y2 is literally either t for t greater than or equal to 0 or minus t for t less than 0, right? So to be more explicit, I've got y1 of t plus y2 of t is equal to t minus t, which is equal to 0, right? for what t? So the top case, like absolute value of t works out to minus t if what? If t is less than 0, right? And this is for t greater than or equal to 0. See that? So these two functions, well, they're linearly dependent, right? Well, they're linearly dependent for positive values. They're linearly dependent for negative values. But what if we think about all values? Right? This is the issue, guys. This matters. This on I business right here, this is actually mission critical to understanding this issue. We have to judge independence of functions relative to some domain. Because it's possible for functions to be linearly dependent with respect to one choice of domain and yet be linearly independent with respect to another. If I just focus my attention on I equal to, say, 0 to infinity or minus infinity to 0, then y1 and y2 are not linearly independent. But if I take the interval of consideration to be the whole reals, then y1 and y2 are linearly independent, right? The reason being, I don't have the same choice of C1 and C2 on the totality of all the points, all right? All right, I've already spent entirely too much time on this issue. Let's go on. My larger point to you, though, is that this assumption, this linear combination being equal to 0, it's not just it's a functional equation, right? So one of the things we can do is we can differentiate this condition, you see? So suppose y1 through yn is linearly independent. Let's differentiate this. What do we get? C1 y1 prime plus C2 y2 prime plus plus Cn yn prime, right? And if you can differentiate it once, you can differentiate it a second time, right? So y1 prime prime, C2 y2 prime prime, Cn yn prime prime, right? Again, this is an equation that holds for all t in the interval of consideration, right? And we're assuming that the functions involved here can be differentiated, right? Although admittedly, that kind of falls flat for my cautionary example 2 example, doesn't it? Because this is not differentiable at the origin, is it? All right, anyway. So that you can continue on this story until we finally get to the n minus 1th derivative. Equal to 0, right? And then if you take all these, right? You got all these equations. This is n equations and n unknowns. We can rewrite this as a matrix, right? So if we write this as a matrix, we've got, y1, y2, yn in the top row, then the derivatives in the second row, and then on down until finally we get to the n minus 1th derivative in the final row, the nth row. Right? Now that times my constants has to be equal to what? 0, right? So we've got 0 on every one of these equations. But this is a linear equation, system of linear equations in the constants C1 through Cn. Right? If we assume C1 through Cn are linearly independent, what is the only solution to this system of equations?
C equals 0.
All the C's are 0. What does that tell you then about this matrix equation? Those of you who've had 221 are currently taking it. What's that? This is a matrix which has just one solution to the homogeneous problem. we should recognize that this is a system of equations with a unique solution. That is to say that this matrix of coefficients must be invertible. That is to say that this matrix of coefficients must have determinant non-zero. All right? So if you haven't had linear algebra already, or just don't remember it, that's okay. I'm telling you what you need to know at the moment, which is simply that I washed my eraser shirt. So I'm going to have to wait a second for the board to dry now. It's like super wet. Ooh, what's on there? Funky. It's got like, see that red? See it? Okay. I'm easily amused. Well, yeah, I mean, of course. What else are you going to erase with? Like an eraser? Like some kind of, punk? Let's see here. So this thing is called the Wronskian. The Wronskian, well, this isn't the Wronskian. This is the matrix. Let me just call this thing M, so I don't have to write it again. The Wronskian, oh man, it's still wet. Stink. All right, fine. Poor planning on my part. The Wronskian of y1 through yn, right? At the value, I guess we were doing t's, right? So t, at t naught is the determinant of like y1 of t naught all the way on out to yn of t naught. That's the top row, and then we do y1 prime of t naught, yn prime of t naught. All right, and so forth and so on. Yn n minus 1th derivative at t naught, the n minus 1th derivative for the last one here at t naught. All right. So you take the determinant of this matrix. This is called the Wronskian of y1 through yn at time t equals to t naught. All right. And what I was just arguing through over there is that if the set of functions is linearly independent, right, then the Wronskian must be what? The Wronskian must be non-zero, right? So, all right. So let's try out the Wronskian for like some functions we care about. Example 3. Let's see here. How about this one? We had like, I don't know, y1 equals cosine t, y2 equals to sine t, and, we could throw in y3 is equal to e to the 2t, just for good measure here. Let's calculate the Wronskian of those. All right, so we want the determinant. Sometimes I omit the t. Hope you guys can deal. So we've got cos t, sine t, e to the 2t here. Then we've got minus sine t, cos t, 2e to the 2t. Then differentiate a second time, I've got minus cos t, minus sine t, and 4e to the 2t. All right. I really regret not making y3 something different, but oh well. I will accept my fate. So we've got cosine of t times 4 cos t e to the 2t plus 2 sine t e to the 2t minus the sine of t, parentheses, minus 4 sine t e to the 2t plus 2 cos t e to the 2t plus e to the 2t sine squared t, finally, sine squared t plus cosine squared t, yay. All right, so if you look at that, there's a common theme here, which is there's an e to the 2t. See that? There's an e to 2t everywhere. So I can factor that out. The top one gives me 4 cosine squared t plus twice cos t sine t. And then I've got plus 4 sine squared t from this guy minus twice sine t cos t. And then finally, the finishing third line, plus 1. So gleefully, these guys be canceling. Whee! And we've got, lo and behold, 5 e to the 2t. All right? So that shows that these 3 functions that I'm looking at are in fact linearly independent, right? Which is super nice because they don't actually have to like work out my definition, right? We just calculate the Wronskian and we're good to go. Now, of course, you could go back to the definition to ascertain linear independence or lack thereof if you wanted to. All right? Now, there's a really neat result that happens for, let's see here. So the theorem, I should probably actually say the theorem. Here's the theorem. If the Wronskian of y1 through ym at x is not equal to 0 for each x in I, then y1 through ym is linearly independent on I. What was the I for my example 3? What's the interval of consideration for those functions? I mean, I didn't write it down, but what is it understood to be? What's the domain of the exponential in sine and cosine?
Positive reals.
Positive reals? That's a little bit cautious. We could be greedier. Yeah, all reals will do it. All right. Here's another one, example 4. If we have the Wronskian of e to the ax, e to the bx, right? Then we're looking at the determinant of e to the ax, e to the bx, a e to the ax, b e to the bx. All right. And calculate that determinant, we got ourselves a b minus a times e to the, well, a plus b times x, right? So what does the theorem tell us? E to the ax and e to the bx are linearly independent on the reals when? What condition do we need? When are 2 exponentials linearly independent?
It's greater than or equal to 0?
No. I mean, e to the minus 2x and e to the minus 3x are still linearly independent. What do I need? I need this to be non-zero, right? How does that happen? What's that?
B can't equal A.
B can't equal A, right? So, yes, 2 exponentials, as long as the arguments are different, linearly independent. Simple as. E to the 2x, linearly independent from e to the 3x, etc. One of the perverse things about calculus over an algebra is this is not true. If you work on like calculus over hyperbolic numbers or something, it's possible for exponentials of different arguments to be linearly dependent because there are other ways to get things multiplying to 0 besides just non-zero things in other algebras, but that is a comment for another day. All right, so here's another theorem that we should work out. So that I have a special calculation in the second. Oh man, I am not planning ahead enough. All right. Well, rats. See, I really want to see you. I want you to see me calculate this. I'm resistant to just putting this on the, oh, look what's happening here. Ah. Oh man. Well, that's just unpleasant. It's okay. Fine, I guess I might as well just accept that. So what I want to look at, guys, is the second order, like an arbitrary second order problem. And I want to show you how we can derive a particular result known as Abel's theorem. And so here's how that goes. We'll start with an arbitrary second order problem that looks like A0, Y prime prime, A0, no, A2, A2 Y prime prime plus A1 Y prime plus A0 Y equals to 0. Okay, I want to study that differential equation. All right. Suppose you have y1 and y2 solve star. All right. Now here, I am not assuming. I'm not necessarily assuming that the A0 and the A1 and the A sub 2 are constants. These actually could be functions in this context, all right? So those could even be functions. This derivation we're doing will still make sense. All right? So, so suppose those solve star. All right? Then let's look at the Wronskian of these. What's that look like? We're just going to call it W because that, there's just one Wronskian here, so fine, W. Big W. It's the determinant of what? Y1, Y2. Y1 prime, Y2 prime, right? And that is Y1, Y2 prime minus Y2, Y1 prime. All right? You guys with me so far? So there's the Wronskian. And then the next step in this this game we're playing is to differentiate the Wronskian. What happens when we calculate like dw? Student's choice. You want me to work in X or T? X, all right. X it is. dw dx. Then this would be what? We've got ddx of y1, y2 prime minus y2, y1 prime, right? Those are products of functions of x, though, so I have to do the product rule. And so if I do that, that gives me y1 prime, y2 prime plus y1, y2 prime prime minus y2 prime, y1 prime minus y2, y1 prime prime. All right? Now, that's just the multiplication of functions here, right? So what cancels? Do you see what cancels there? So like this guy and that guy, gone. And we can do a little bit more, right? Because we've got y1 and then I've got y2 prime prime, all right? Minus y2 and then y1 prime prime. But we are assuming y1 and y2 solve star, all right? So that means that I have a little bit more to do. I have two things to work with. I have a2 y1 prime prime plus, actually let me put a j there. A2 y sub j prime prime plus a1 y sub j prime plus a sub 0 y sub j equals to 0 for j equals to 1 and 2, all right? I have both of these functions solve it, right? And there's a little bit more that I haven't told you yet. For this to be a genuine second order differential equation that's of the ordinary type, we also need to know that a sub 2 is non-zero. So I can divide by it, okay? So if I solve for like y2 prime prime, I get, minus a1 y2 prime minus a0 y2 all divided by a2. And likewise over here I get minus a1 y1 prime minus a0 y1 all divided by a2. So what I did was I just solved the fact that I solved the differential equation for the second derivative for both solutions, and I plugged it in here, all right? Oh, look, stuff cancels again, because we get like, if you look at it, does stuff cancel? What cancels?
First terms of each conditions.
You sure?
So, no, I'm not sure.
Hmm? Right. I mean, that's what I was thinking also, and I was wrong. Exactly. See, because if we look at this and that, if we look at this and that, when they multiply, we get y1, y2, or we get y2, y1, but that's the same thing. And they're both having the, a0 over a2, both of them, right? Those cancel. And we're left with what? We're left with the ratio of a1 to a2. Oh, I'm sorry, this hideous Carolina blue. Get it away. The ratio of a1 over a2, there's a minus, I think. And then we've got y1, y2 prime minus y2, y1 prime, yeah? But that is what? What is that?
Product rule between.
No. Look up here. Yeah, that's the Wronskian. So we have minus a1 over a2 times w. In other words, we face dw over w is equal to minus a1 over a2. These could be functions, dx. Integrate both sides, and we've got ourselves a w is equal to some constant times the exponential of the integral, of minus a1 over a2 dx. This is known as Abel's formula. The significance of this for the theory, guys, is that if the Wronskian, so see how this works? Could you have a Wronskian for a solution set, right? If you have y1 and y2 solve a differential equation, could you have the situation where for some points in the domain the Wronskian's 0, but for other points in the domain the Wronskian's non-zero? Could that happen here? See, it can't happen because we have this formula. This formula says the Wronskian is either identically 0 because the constant k is 0, or it's non-zero. So for a solution set, we must have the property for the Wronskian of the whole solution set that it's either identically, that if it's non-zero at even one point, it's non-zero at all points in the domain of definition for your solution set. Which is actually what we saw in example 3 actually would be an example of a solution set to a particular differential equation, although that would be a solution set to a third order problem, all right? Okay, so let me use the projector here for a second because I got a lot to tell you theory-wise, and you don't want me to write it out, I don't think. And also, top of the hat to you. Let's see here. I can find my hat. All right, come on. 4909. 4909. All right. I hope you guys enjoyed the Surprise Attack Mission 2. I thought those problems were not too bad. The vector field one was a little bit fussy, but Is that light switch actually functional back there? Ah, yes. Yeah, if you could hit some of those. I guess it's an all or nothing kind of deal, huh? All right, well, if you guys won't go to sleep, we'll stick with this. I guess even if you do, I won't know. All right, so we are, of course, in chapter 3. And so to start with, I set the stage by defining the arbitrary nth order differential equation in this form, right? We talked about this already. In this case, you can rewrite it as an operator, right? With the coefficients, As I talk about, we can rewrite that as an operator like this. We can introduce the operator, which is like, a0 times d to n plus da 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 plus all the way down to a sub n. My apologies here. I have, for reasons I forget, numbered the coefficients in opposite the order I just did. And I really don't like this numbering, and I need to eradicate this from the notes, but I have yet to devote this notation to destruction, so it still persists. But beware, I have stupidly numbered from 0 to n as opposed from n to 0 here, but whatever. I hope you can see the pattern. Now, first of all, big theorem, if you have such a problem, if you have continuous coefficient functions, and your leading coefficient, which in this notation is a sub 0, and my other notation would be a sub n, if it's non-zero for all x in the interval of definition, well, guess what? If you have initial conditions, n of them, well, then there exists a unique solution, which is a function that you can plug into the differential equation. It works. And that function will satisfy those n initial conditions, all right? So this is the existence and uniqueness theorem. And, if this was a math class, we could prove it if we had 2 weeks and a background in real analysis. And I had the support of the chairperson for when the students rebelled. Stuff like that. But anyway, okay, we defined this today. This is linear independence. Let's go on. That's the Wronskian. We talked about that already. That's the formulas for the determinant if you didn't know it already, but you know it because you had Calc 3. Here's some more calculations. So this one here is kind of fun to just stop and think about for a second. This is the Wronskian of x, cosh, and sinh, right? This works out to x, all right? Minus x. What that means, if you believe the Abel formula, is that x, cosh, and sinh cannot be the solution set for a third order differential equation on the whole real line. Because if it was, this couldn't be 0 at 0. So this could only be the solution set if our context doesn't allow 0, in which case your Wronskian would be identically non-zero. Now you'd be like, well, you've only proved Abel's formula in the second order case. It seems like you're saying it works in the nth order case. Yes, I am. This is the calculation we just went through. Here's the formula for the Wronskian for the n functions, which I'm using big Y's for so it's easier to look at. That's just a formula for it. That's the completely anti-symmetric symbol. That's a stone cold formula for the determinant, which you can differentiate and use the n-fold product rule like such, and then do some arithmetic and substitute the differential equation back into the thing. And after about a page of calculation, guess what? It still happens. It's still the case that the derivative of the Wronskian is minus the ratio of the coefficient functions times the Wronskian again. So Abel's formula is not just a second order case, it's actually an nth order case. And don't worry, I'm not going to test on that calculation, right? Yeah, you're welcome. That calculation still works in the calculus over an algebra, though, by the way. I worked on this with a student a few years ago, but anyway, more on that later. But so here's our definition. We have an nth order problem. We say S, a set of n functions, is a fundamental solution set if when you plug if it's a linearly independent set, and these are all solutions to the homogeneous problem. So the differential equation has possibly a non-zero f. The so-called inhomogeneous term can be non-zero, but the homogeneous equation puts a 0 there. So we're looking for n homogeneous solutions to form our fundamental solution set. Once you find that, here's the deal. If you have an nth order linear differential equation with continuous coefficient functions on interval I, Well, this theorem actually tells us that our search is not vain. There is a fundamental solution set to find, all right? And this is essentially a corollary to the existence and uniqueness theorem that I stated about 2 minutes ago. Basically, you just judiciously pick your initial conditions like this, and when you plug those initial conditions into the Wronskian matrix, you've got the determinant of the identity matrix, which is non-zero. Therefore, yay, we can do it. That's the proof. The thing I'm actually interested in is this one, though. Did I ever move? Yeah, I did, okay. If we have an nth order linear differential equation with continuous coefficient functions on an interval I with fundamental solution set y1 through yn on I, then the solution of L of y equal to 0 can be expressed as a linear combination of the fundamental solution set. Notice here, there's no f, right? I'm just talking about the homogeneous problem. This says that any homogeneous problem of nth order you can write as a linear combination of n fundamental solutions. All right? So our problem then for a given differential equation is to find these fundamental solutions. Spoiler alert, we already did it. You write the differential equation as a polynomial and you factor it, and then you write down solutions from the factoring. That's how we did that. That's how we found those fundamental solutions. And then finally, if we have a non-homogeneous problem, which is what we're about to dive into, L of y equals to f, it turns out that the general solution there can be built from two pieces. One is what's called a particular solution, because if we plug it in, we actually get the inhomogeneous term. But then also, this piece over here, these are all homogeneous solutions, so this piece all will go to 0 if we plug it into the linear operator. But the y sub p gives us back the f. And so this is the generic form of our general solution. So that frames the discussion going forward. That's what we're up against. We need to find, oops, maybe I'll take the lights again, thanks. Oh, hey, there were two switches. All right, but yeah, good morning. All right. So, listen guys, for the constant coefficient problem, I've already showed you basically my bag of tricks for finding the solution sets, all right? So the next order of business is how do we solve non-homogeneous problems, right? And so there are two methods, basically. The one is undetermined coefficients, all right? And the other is what's known as variation of parameters. Variation of parameters is general. If you have any linear nth order problem, if you can find the homogeneous the fundamental solution set rather, variation of parameters gives you a method, formulas indeed, that if you calculate certain integrals, you can write down the general solution. But variation of parameters comes at the cost of integration. Now, undetermined coefficients, on the other hand, we can just do with just algebra, but its application is limited only to the problems which essentially have forcing functions, which are more or less the same kind of things we've already seen for solutions to constant coefficient problems. All right. So let me show you. Well, first of all, the theorem is just this: is given L of y equals to f. With a fundamental solution set y1 through yn such that L of y sub j is equal to 0 for j 1 through n, and L sub yp equals to f, then y equals to c1y1 plus da 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 plus cnyn plus yp. That right there, my friends, is the general solution. All right. So let's look at this problem. What example am I on? I try to remember. 4, 3, 4, 5. Oh, whew. Time flies when you're having fun, I guess. So all right. So example 5. Suppose we're up against y prime prime plus y is equal to, let's say, t squared. All right. So we know the deal. This is lambda squared plus 1 equals to 0, which tells me that lambda is plus or minus I. That's my characteristic equation. And from this, I can cipher y1 cos t, y2 sine t based on our previous lectures, okay? Those are my fundamental solution set, sine and cosine. I plug those in, they would give me 0, right? They're certainly not going to produce that t squared that we need. So the naive thing to do here is just to go, well, if I differentiate t squared, I get 2t, right? And if I differentiate it twice, I get a 2. Maybe if I look at an arbitrary quadratic in t, maybe that would work, right? So we take a guess, and we make a naive guess. Yp is like a t squared plus bt plus c. Just do a marker. Oh well, short, I think. So this tells us that yp prime is 2at plus b, which then tells us that yp prime prime is 2a. Plug it in, yp prime prime plus yp equals to t squared gives me 2a plus at squared plus bt plus c equals to t squared. If it's going to be a solution, it's got to work. How do you find it? How do you make it work? Plug it in and see if you can adjust the constants, the undetermined quote-unquote coefficients a, b, and c, so that it works. Is it going to work? Well, this tells me what? Equating coefficients, I get a equals to 1, b equals to what's my, do I have any t's over here?
No.
So b is 0. Constants, I've got 2a plus c equals to 0, so c apparently is minus 2. Lo and behold, my general solution has the following form. c1 cos t plus c2 sine t plus t squared minus 2. Solved. That is the general solution to this second order non-homogeneous problem. Sometimes it's as simple as this. We simply guess the particular solution has the same form as the inhomogeneous term, right? Sometimes this works, until it doesn't. So let me show you a cautionary tale. We'll try something similar on my second example and see how it goes. What if we're up against, say, y prime prime? Minus 3y prime plus 2y, and we'll make it equal to, I'll do it x this time, e to the x. Right? So this, notice, is lambda squared minus 3 lambda plus 2. Factor that thing. So I get y1 is like e to the x, and y2 equals e to the 2x. There's my fundamental solutions. My fundamental solution set's just exponential, e to the x, e to the 2x in this case. Now naively, what would we guess if my inhomogeneous term is e to the x, right? And let me clutter it up a little bit more. Let's not just do e to the x. Let's do e to the x plus plus x, right? Then that would suggest to me we could let yp be something like a e to the x plus bx plus c. See, because if I differentiate x, I can either get a constant, or there's also an x there, right? So naively we put bx plus c. But what happens with this, when we calculate yp prime, we get a e to the x plus b, and yp prime prime is, well, a e to the x, right? take those, plug them back into the differential equation, what happens? We get, you know, I'll write it out. I usually write it out symbolically once to try to keep myself on the straight and narrow here. I might not have done it last time, but I'll do it this time. So we want yp prime prime minus 3yp prime plus 2yp equals to e to the x plus x, right? And is this gonna work? I don't know. Like, let's find out. Well, it's not gonna work. I know it's not gonna work. That's why I did this. But ae to the x minus 3 times yp prime. Well, yp prime was ae to the x plus b, and then 2 times, well, what was it? ae to the x plus bx plus c equals e to the x plus x. Yeah. And some of this could work out okay. I mean, if you focus on the terms that are, you know, involving the x, the a, and the like the bc terms, they're okay. You know, if you look at this here, and this here, and this here, and this here, just focusing on that piece alone, it suggests that like minus 3b plus 2c is equal to 0, and also that 2b is equal to 1. So apparently b should be 1/2, and c should be what? Yeah, 3/2 of b, right? I think it's 3/4, isn't it?
Yeah.
Now, in order to believe this calculation that I just did in blue, you have to suspend disbelief, though. See, because there's other much worse things that are going on in this calculation, which are what? So if you do this, then everything with x cancels, and what are you left with? You're left with ae to the x minus 3ae to the x, right? Plus 2ae to the x is equal to e to the x.
There's an extra x connected to the 2b.
That's why I have the 2b equal to 1, because this 2 times that b has to match that.
Yes.
So, yeah. But notice the exponential terms. Ooh, that's a bad. That's 3 minus 3, which is 0 equals e to the x. Oops. So,
Natural log of 0 equals x.
yeah, this is not allowed. I mean, it is true. You can try it out. That if we put yp1 equal to, like, you know, 3/2, not 3/2, 1/2 x plus 3/4, right? This guy, that solves yp1 prime prime plus, rather minus thrice yp1 prime plus 2yp1 equals to x. Like this, you can check that's true. But this exponential term, something funny is going on, isn't it? Why is that? What's the difference between this example and the previous one? How did I get back to example 2? Good grief. 6 maybe, okay. So here's the issue. There's a very, very big difference. In example 5, the homogeneous terms were cosine and sine. The inhomogeneous term was t squared. They have nothing to do with each other. They're independent. Here, the homogeneous solution's e to the x. The e to the x here, and that e to the x. I call this phenomena overlap. Whenever there's overlap, the naive guess fails. But it doesn't have to fail completely either, right? Like, part of the naive guess worked. So what we're going to cover next, guys, is called the method of annihilators. The method of annihilators will use the operator calculus to derive the correct form of the particular solution. And in the process of doing that, we'll also gain a much deeper understanding of the homogeneous problem. So anyway, I'm a little bit behind at the moment, but we'll catch up. So sorry, guys. Well, not sorry. I mean, I have no regrets.